So, good evening to everybody present here. First and foremost, thank you all for coming. Second, a show of hands for the people who attended yesterday's lecture, please. And a show of hands for the people who could not attend. And how many of you, please keep your hands raised. And the people who watched the lecture, please put down their hands. The lecture that was sent yesterday. So, yesterday, somebody, Harshad. Okay. So, were you present in yesterday's lecture?
Yes.
What all did we cover? Do you mind reminding me?
We covered set, cardinality of set, subset, and operation of set, intersection and union. And we did some part of function. 1 and 1 2 function. Injective or subjective. Even it was also the question. Gradient and degree.
That was all. As for the functions part, I was just trying to show you what we are supposed to do. But yeah, we'll do that today. And I put up a poll, and I believe a lot of you had problems in some part. So a show of hands to the people who had some trouble with the definition of set. But still, I believe that a few people here are attending for the first time. And I give them that liberty because, of course, like I said yesterday, there were some logistical issues with the lecture hall. So I would take a minute to tell you what a set is again. Might help the others review as well. So a set is a well-defined collection of objects. That's all a set is. And if somebody wants to make notes or anything, I'd say one again, the definition of set, or at least I would like you to quote it as the naive definition of set is a well-defined collection of objects. And when I say well-defined, what I mean is that all people must agree on what the set is. We discussed an example that if I was to tell you to write a set that has only one object inside it, and an object which belongs to a set is said to be an element of the set. Yet again, for the definition, I would repeat, an element of the set is an object which resides inside the set. So if I was to tell you to write a set that has just a single element in it, or say the best batsman, so all of you would come up with very different sets. But if I was to tell you to write the set of all natural numbers less than 5, all of us would write the same set. So when I say well defined, that is what the set means. I also talked about why that definition does not work, but we will not go into that because you do not need that. And a show of hands for the people who had some trouble with the representation. But I would review it anyways. We discussed two representations of set, one being the roster form and the other being the set builder form. So I repeat, and if somebody wants to note down, a set can be represented in two ways. One is the set builder form, the other is the roster form. If you remember, I also mentioned tabular form. Tabular form is just another name of the roster form. I wanted to take a moment to clarify that. A show of hands to the people who had some problem with subsets. Okay. I would define it anyways. So let's say I have a set A and I have a set B. These curly brackets are used to denote sets. The elements are written separated by a comma. So 1, 2, 3 are elements which belong to A, 1, 2 are elements of B. So if you notice, every element present in B is also present in A. Thus, we say that B is a subset of A. Well, I just wanted to make the word dash, that does not mean anything here. But B is a subset of A. That is how we denote it. And if somebody wants to note down a definition, B is said to be a subset of set A if every element that belongs to B also belongs to A. That is, 1 and 2 belong to B and thus they also belong to A. So B is a subset of A. In easier terms, in layman terms, anything that you see inside B, it comes from A. So B is a subset of A. And then I talked about the subset, and then I took a moment to show you that every set is a subset of itself. We discussed a few properties, one of them being every set is a subset of itself. And though this may seem counterintuitive, but if you look at the definition, it works, because every element in set A does belong to set A. It comes from set A. If somebody wants to note down, the property of subsets is such that every set is a subset of itself. Then we defined an empty set, which is given by the Greek letter phi. This tells me that this is a set, and nothing in between tells me that this is a set which has no elements. And I talked about why it is well defined, because a set needs to be well defined. So if I ask any of you to define a set that has no elements in it, all of us would write down this exact same set. And did I review the representation? No, I did not properly review the representation. As for the representation, I told you there are two ways to write down a set, one being the roster form and the other being the set builder form. So in the roster form, this is the roster form. You write A is equals to set, this curly brackets denotes a set, and you write the elements separated by the comma. You enlist all the elements of the set. If the set is infinite, you denote it. For example, if I was to write the set of all natural numbers, I would write 1, 2, 3, and I would leave some dots that tell me and so on. So if I naturally follow this sequence, I know the next element is going to be 4, after that 5, and so on. So this is the roster or the tabular form. Coming now to the set builder form. The set builder form is written in this manner. A is a set, and I write X here. So it reads A is a set of all X. So whatever condition that I specify for this X, every X that specifies that condition must reside inside this set. This is the symbol of X such that this represents such that. In a lot of references and textbooks, you'll find a colon. The colon means the same thing, that is such that. And if this means belongs to, so X belongs to natural numbers. This represents the set of all natural numbers. This is this set here. And X is less than 6. So there are two conditions. The set of all X's such that X belongs to the set of all natural numbers and X is less than 6. So what possible X's are these? These are 1, 2, 3, 4 and 5. So if I was to write the same set in the roster form, I would write A equals curly brackets 1, 2, 3, 4, 5. This. Now talking about the empty set. By definition, empty set is the subset of all sets. And I can prove that. Because if you look at the definition of a subset, it says that every element that lies in A must also lie in B. So every element that lies in the empty set does lie in B because there is no element in the empty set. So it does satisfy the condition such that the empty set is the subset of all sets. Did anybody have any problem with the operations? Okay. So on sets we define two types of operations. One of them being union and the other being intersection. So union for two sets, let's say there exists a set A and a set B. So A union B is defined as the set of all x's such that x belongs to A or x belongs to B, which means that any x that belongs to A and any x that belongs to B or any x that belongs to B must belong to A union B. That is, if I was to illustrate the same example here, that is A is the set containing 1, 2 and 3 and B is the set containing 1 and 2. So all x's that lie in A, that is 1, 2, 3. So 1, 2, 3 must belong to A union B. And then there's B. 1 and 2 lie in B. So 1 and 2 must also belong to A union B, but we already took that from A. The intersection is the same thing. By the way, the union is denoted by a U. The intersection is denoted by an inverted U. And here it becomes very good. And x belongs to A and x belongs to B, which tells me that all x's such that x must belong to A and x must belong to B. So for an element of A or B to exist or to belong to A intersection B, it must belong to both the sets. So if I look here, 1, 2, 3 belong to A and 1, 2 belong to B. So what elements belong to A as well as B? That is 1, 2. So A intersection B, so this particular AB would be the set containing 1 and 2. As for the cardinality section, we would discuss functions today, and we will discuss injective functions, surjective functions, bijective functions, and based on that, we will be defining cardinality. So I'll let you be for the moment. Another thing that I missed is that you guys do recognize Varun from last class, right? He's sitting at the lab. Varun, could you please stand up and dash?
So never lets me complete my accelerated activities.
So Varun would like to take a moment to speak to you. Please, Varun, go ahead.
So yeah, similar to his sessions, like he's taking these sessions to teach you guys about mathematical prerequisites for classical mechanics. Similar to that, I believe, at least people around me, they had a very weird presumption about, specifically inorganic chemistry, that it is something that's not very logical per se, but I feel like that perception should be changed. And this is what I'm going to try in my sessions, that I'll be starting from probably the next weekend, maybe before or after his sessions. My sessions won't be that long, of course, for the initial time being, because your course is anyways very basic and I'm just trying to bridge the gap between you and the instructor, because I feel like many of you would have a feeling of feeling that gap between you and the instructor. So yeah, that's all. I'll be starting those sessions on from the next weekend, probably in the AB. If I get hold of an LH, I'll surely do it. Thanks a lot.
Thank you all. Okay then. So now that we are done with the review of sets, any questions regarding sets? Yes, ma'am.
Sir, I want to ask if you can also explain countability again.
Yeah, I'll come to countability, but countability relies on cardinality, which relies on bijective functions. So we'll also discuss cardinality today. However, I remember that the maths people, I asked you a question yesterday. How many of you figured it out? I asked you that why does d dx sin x equals cos x apply only to radians? Anybody could figure it out? It's fine, it took me around a week as well. So if any of you can do it before the third lecture, I'd consider you smarter than me. Okay then. So usually the way we do things is, in order to get to a function in a mathematics course, first you go through relations, sorry, not even relations. You start with something that's called a Cartesian product. Then from the Cartesian product you define something that are called relations. And then from the relations you define functions. But I want it to be the other way around. Because I do not want that when I'm teaching Cartesian product and relations, you're going to wonder why is he even doing that in the first place. I want you to understand, it's like, because we already know what's going to happen, I'll tell you what am I looking for, and then I'll go on a journey to find it. Is that clear to everybody? So, so basically, though I'm not able to draw it perfectly, all I'm trying to do is this is a circle centered at the origin, and the entire region inside the circle, the region bounded by the circumference of the circle, is shaded. And then I ask you a question: is this a graph?
Yes, sir.
Okay. And why is it a graph?
Because it lowers inequalities.
Exactly. It is a graph of an inequality. The inequality being, so we will discuss it later, but all I'm trying to say is, what is a graph? A graph is the set of all points, at least a graph in the Cartesian plane, because the definition of graphs are going to change when you start dealing with n-dimensional space, vector spaces. But anyways, the graph, when I talk about the graph of, let's say, a two-valued function in a Cartesian plane, it's the collection of all points that satisfy either an equation or an inequality. So that is what I wanted to say. And thus, now that we understand what a graph is, somebody from the second last row there, sir on the corner, what's your name? Sorry?
Harshvardhan.
Harshvardhan. भाई हाथ में पीछे किया हुआ है यार, normal. Harsh, do you know what a parabola is?
Yes, sir.
What's a parabola? How does it look?
It looks like.
So you're saying it looks like this? Okay. And no, that is not a parabola at all. It should be symmetric about the y-axis, but you get the idea. So thank you, Harsh. Sorry?
Harshvardhan.
Harshvardhan. Thank you, Harsh. So Harsh tells me that this is the graph of a parabola, and I claim that this is the graph of y equals x squared. I said that graph is the set of all points. You may say y. The graph is the point. Graph is the set of all points in the Cartesian plane, such that this is the set of all the points which satisfy this equation. So I know that the point 1, 1 does lie on this graph, or is an element of this graph, because like I said, a graph is a set. A set has elements. So 1, 1 is an element of the set which represents this graph. Now that I've told you the graph is the set of all points, and I want to talk about a particular graph, what you will notice is that all that's happening is that for every x, I'm getting a y. And another thing that we discuss tomorrow is that what we are trying to do is, we are trying to create a box which we are going to call function. For those of you who are attending for the first time, this is Aditya Khurana. He's my best friend and my mentor here at IISER Mohali. So, in this machine, you send an input and you get an output. And I told you that for each input there must exist only one output. Very good. So, in a similar manner, what I can claim is that this set, the set which represents this graph in the Cartesian plane, is the set of a comma b's, because these represent the coordinates of the points that are in the set. All a comma b such that this is the symbol for the set of all real numbers. So this is the set of all ordered pairs. When I say ordered pairs, what I mean is that the order matters. A comma B is not the same as B comma A. For example, I have another point right here, which is -1, comma 1. And what exactly do I want to do? Let's say this is not the graph that I will describe it with, but let's say if a graph has the point 2, comma 4 as well as 4, comma 2, those points would be different because 2, comma 4 is 1, 2, 3, 1, 2, 3, 4. It would be somewhere around here, and 4, 2 would be 1, 2, 3, 4, 1, 2. It would be somewhere around here. As you can see, these two are distinct points. So such a thing is what we are trying to get. And if you look at it, it is the set. It is in some sense, if I treat this entire thing, if this whole plane per se, so the plane has all the points in it, and we are trying to choose a subset of the plane as a graph, right? So we want to choose a subset from this larger set such that what are the elements? The elements are ordered pairs which follow a special rule such that for each A I get just a single B. So what we are trying to do is, since we are trying to consider ordered pairs, we'll define something between two sets that has all the possible ordered pairs of the set. Fine? Because the first step is you want all the ordered pairs, and then you choose particular ordered pairs from it, right? So the way we are going to begin on this journey to define a function mathematically is to first define all the possible ordered pairs.
Excuse me.
Yes.
Why did you use the word inequality for the graph?
Inequality, because I'll prove this as well some later time, I hope. If I have a point x comma y in the coordinate in the Cartesian plane, its distance from the origin happens to be under root x square plus y square. Alright? And let us say I put a bound that this must be less than equal to a. So what it means is that I want all the points such that their distance from the origin is less than a particular distance. I'm treating a as positive. If you want a to be any number, any real number, I would like you to put a mod, and we'll also discuss mod if you do not have it. But the function of a mod is to make numbers inside it positive or at least 0. So let's say this is a. So if I draw a circle here, every point inside it, all these points, would actually satisfy this inequality, because all the points inside this have their distance from the origin less than or equal to a. Now, as I said, I would like to define all sorts of ordered couples between A and B. So let us say I have a set 1, 2, 3, and I have a set B 4, 5, 6. So I would like one of you to tell me at least 3 ordered pairs such that 3 ordered pairs A comma B such that A comes from the capital A and B comes from the capital B. Yeah, please.
142536.
142536. What's your name, ma'am?
Ananya.
Ananya. Okay. So, like Ananya said, what the elements 1, 4, 2, 5, and 3, 6. So basically, what we are doing is we are taking an element from here and we are taking another element from here, so that we are getting an ordered pair. So what we are going to do is, in order to get all the possible ordered pairs, we'll take one element from here and then we'll couple it with each of these elements. We'll take the second element, couple it with each of these elements. The third element, couple it with each of the elements. So what we're going to get is we are going to get 3 elements here with that have A equals 1, 3 that have A equals 2, and 3 that have A equals 3. So therefore, though this is not very important, but for a Cartesian product, this means a Cartesian product. This means the set of all the ordered pairs AB such that A belongs to A and B belongs to B. As in, the small letter A belongs to capital A, the small letter B belongs to capital B. So as you see, we take each element and we get another element that we in some sense we take each element and we couple it with each element of B. So the number of elements in A cross B is the same as number of elements in A multiplied by number of elements in B. Here NA is 3, NB is 3. So you will have a total of 9 elements in A cross B. So now we have defined A cross B. And if you want to note it down in terms of sets or the set beta form, I will write A cross B is the set of all A comma B such that A belongs to A and small b belongs, or the lowercase b belongs to the uppercase B. This is A cross B. Now what we are going to try doing is, we'll extract some subsets of it. Though it is not necessary for defining a function, but there's something also called relations. So I would like to talk to you about relations as well. So let us say I have A cross B and I choose a subset of A cross B. A subset of A cross B is defined to be a relation defined from A to B. Any subset of A cross B will be taken as a relation defined from A to B. And now I would like to introduce you to another notation which would help us with this coupling rather than writing out the terms every time. That is, we draw two, Venn diagram. So it's a Venn diagram that we are looking for. We are looking at a Venn diagram, and well, Venn diagrams are typically not this. There are different things, but these are loosely called Venn diagrams. Venn diagrams are generally, I'll show you what a Venn diagram is. Let us say I have a set A and a set B, and both of these are a subset of a larger set which I call the universal set U. The universal set U has all the elements that I am concerned about. So, uppercase U is the universal set. A and B are subsets of the universal set. So, this entire region, every element that lies here tells me about the set A. Every element that lies here tells me about the elements lying in B. So, if you look at it, here we have all the elements of A, and here we have all the elements of B. So, union and intersection are easier to think about when you think in terms of Venn diagram, because A union B tells me all elements such that they either lie in A or B. So, if I shade this entire thing on my Venn diagram, this represents A union B. And A intersection B means the set such that an element that either lies in A as well as B is part of A intersection B. So that would be here in the overlapping region. Using these in sets, there are things called complements, and you use them a lot when you study probability and statistics. But I do not want to go into that as of right now, because that is not much use to us. So where was that? So we draw two kind of ellipses. You can draw anything. This is just convention. If you look at some books, they'd rather draw a cloud representing A and another cloud representing B. So let us say A has the elements 1, 2, 3. So I write them vertically. Let us say B has the element 4 and 5. I write them vertically in B as well. So like I said, a relation is the subset of the Cartesian product. If I was to in some sense represent the Cartesian product, that is every element is coupled to every other element, what I would do is and this arrow shows that they are being mapped. This is what we call a mapping. So a Cartesian product is such that you map all the elements from A to all the elements in B. Are we clear till here? Now if I take a subset, that is, I could remove a few mappings out of it. Let us say, I just keep 1 goes to 4 and 2 goes to 4. This is a relation. And like I said, because a relation is a subset of a Cartesian product, between two sets, we can have multiple relations. And now that we have this, I would like to ask one of you the definition that we gave for function. What is missing here?
One input is giving 2 output.
Anybody from this side, please?
Two inputs are there.
Two inputs are there, but input can be anything. For example, if I draw the curve,
Not giving any output.
why is this dot square?
not as an input.
I have got the entire x-axis as my input. Somebody from the left hand side, please. Sorry? No, even same output is not a problem because in y equals to x square, if we accept it to be a function, 1 gives me 1 as well as minus 1 gives me 1.
Three
Somebody from the left hand side. Anybody, please. I would like the class to be as interactive as possible. Somebody.
Giving many outputs.
No, giving many output is no other problem because if you look at it, even here we have got multiple outputs. Like for every y greater than or equal to 0, I could give you an x. So this entire thing is my output here. So outputs, having multiple outputs is not a problem for the definition of a function. Anybody else?
All the inputs is not giving an output.
Yeah. Sorry.
Yes.
Very good. Now you guys are interacting with me. You know, I get bored very easily, so please keep interacting. Or I teach you something wrong and you'll live with that concept for a very long time. So, if you look here, now I can claim that this is a function. So, what defines a function? From A to B, we show it like this. If I name my function f, just like I can name my set anything, I can call it A, B, C, Z, whatever I feel like calling it. In a similar way, if I call my function f, what f does is, or what f is that it takes, because f is being defined from A to B, I would like to introduce you to this subtlety, that is f defined from A to B and f defined from B to A are two completely different things. Are we clear on that? They can be equal in some instances, but they need not be equal. So if you are defining f from A to B, what I need is that every element of A is coupled to exactly one element in B. And when I talk about exact coupling, they could be coupled to the same element, but they should not be coupled to two elements. And this is a relation, but this is not a function. Because you remember all the mapping, it's A cross B. And then any subset of that mapping is a relation. So this is a relation because it has a subset. We see some couples. And for that matter, even if we did not see any couples, we could still call it a relation. Because if you remember that the empty set is the subset of all sets A. So the empty set is still a subset of A cross B and it's still a relation. Or at least that is what I remember. Does the definition say that we need it to be non-empty? Any of the math students, please? No, we don't need to be non-empty. Fine, I'll make a note. I'll make sure I remember that. So I need to know whether an empty set can be a relation, but that's just a matter of definition. If, because like I said, we define things, that is why I told you in the first day, we define things and we work accordingly. So if I define a relation to be any subset of A cross B, that would mean that phi is a relation as well. But if I define it to be non-empty, that then all subsets of A cross B except for phi would be a relation from A to B. And now we have finally defined the function, which is the beginning part of calculus. And as Professor Gautam Sheikh would say, if you understood nothing until now, it's still fine, you have lost nothing. So most of it, we did it for no purpose, it's fine. If nobody attends the classes until this point, if they do not see the lecture, they could still work out. But what I would also like to mention is that what you have gained is something that we call mathematical maturity. That is because, like I said, in mathematics you can define anything and deal with it. So what we have understood is that once we define things, how do we logically deduce those things? Physics is the same as mathematics, loosely speaking of course. It's just that rather than our axioms coming from our common senses and our convenience sometimes, the axioms or the postulates, they come from nature and observation. For example, all of you would have studied Newton's laws, the 3 laws. We have no proof for them, just like we have no proof for this fact, that if these angles do not add up to 180, that is, if I call this theta 1 and theta 2, theta 1 plus theta 2, if they do not add up to 180, L1 and L2 are not parallel lines. When extended on both sides, they will intersect at some point. But you cannot prove it, you simply believe in this. In a similar manner, you cannot prove Newton's laws, you believe in them. If I was to ask you, I'm deviating a bit, but of course it says for physics it's not deviating. If I kept a block in front of you of whatever mass m, there's a 5 Newton force here, there's a 7 Newton force from here, and let's say it's not kept on the ground, it's kept in free space, in a vacuum. This is an isolated system, it has no interaction with the outer world, the external world. What is the net force on this block? Are you convinced? Along which direction? You're telling me that the net force of this should be 2 Newton. Why?
Because the stronger force will overpower the weaker force.
No, I get that you are doing an addition that is 7 minus 5. But why must the net force be the sum of all individual forces? A lot of you are claiming principle of superposition. Can you prove principle of superposition to me?
Experimentally.
So you believe in principle of superposition.
Yes.
But it does work. Which means in physics we have axioms as well similar to these. It's just that they come from nature, they come from experience, they come from observations. So that's what I was getting to here. So now, as far as I can remember, I have a very weak memory, so one of you will have to remind me where I was at. But now we have defined functions finally. So I will need somebody smarter than me to stand up and tell me what a function is, because like I said, I have a weak memory. So somebody from you're sitting at the very back, sir, or you raise your hand, sir. You will get your opportunity as well. So you raise your hand. What a function is? What is a function?
It's like a machine. Like if you give an input and that it tries to give an output, or it will give an output.
How many outputs?
It can give multiple outputs. It can.
No, it cannot. If it's giving if it's giving
Yeah,
multiple
it's not
outputs, it's a
a
relation.
function.
A
Relation.
function.
Yeah.
This is not a relation. This is not a function. Now it is a function. But that is the machine that you talk of. It needs to give you exactly one output. Also, the machine is broken if it can process strawberry ice cream but not vanilla ice cream. Which means that it does not need to take elements from a set and give me elements from another set. What it also needs to do is, it needs to be capable of doing that procedure for each and every element of the set. So now we have defined functions.
Excuse me, sir.
Yes.
Is it necessary that all the inputs give only one output?
No, not at all. No.
One input should give one output.
Yeah, one input should give one output. They may be same, they may be different. We are now done with functions. And I know the math students might be getting bored, but I am holding on to you because we still have to discuss countability, and more importantly, like I promised in the last half an hour or so, we'll be discussing inertial and non-inertial reference frames, which would tell me, which I have heard that some people are having some difficulty comprehending. I'll have a break in a few minutes.
Excuse me.
Yes.
When we define function, do we say that it needs to give us one output for all the inputs, or it needs to give us one output for some inputs?
All the inputs.
All the inputs.
Yes. For example, if I was to define a function from the set of all real numbers to the set of all real numbers, it would only be called a function if I took an element and I always got exactly one element from the other set. And now, I would also like to define some terminology, and terminologies are boring, that's why I keep forgetting them. But these are very basic terminologies, so I hope you will remember them. And even in case you forget, like I said, we are mathematicians, we rely on logic, not on something else. We are not chemists, but we are mathematicians, so we do not rely on anything other than logic. So in case you forget the definition, you can always look it up, and then using your logic, you can always reach the same results. So when we define a function, there's something called a domain, there's something called a range, and there's something called a codomain, for which I would like to draw a function for you. This is a function from the set of all natural numbers. No, I do not want to deal with an infinite set right now. Let's just deal with a subset of natural numbers. That every element in here comes from the set of all natural numbers. And let us deal with another set of another subset of natural numbers. So they've got 1, 2, 3, 4 here, they've got 5, 6, 7, 8 here. So this, if I define a function from A to B, and remember the direction of the function is important. If you define a function from A to B, that does not that does not exactly tell you that you could always define the function other ways as well, but these would be two different functions. F from A to B and the same F from B to A would be two very different things. And we'll also see, you wanted to ask a question? And we'll also see examples of those. So, like I said, if I'm defining a function from A to B, every element of A needs to be mapped. And this set I call the domain. B does not have the same limitation or restriction. It is not necessary that I need to map every element of B when I define a function. So if you look at it, only 5, 6 and 7 are mapped. So the subset of B for the function f, the subset of B such that it is getting mapped to some element of A. This subset I call the range. And it's going to help you if I give you a familiar example. That is, if this is y equals to x squared, though it does not look like a parabola, the domain is all x's. For every x, I can find out a y. This is my entire domain. And then, when I map it, this was the set that I was mapping to. I have not given you the terminology for it yet. But this was the set I was mapping to. However, only this subset of it has got mapped. That is, for a negative y, there exists no x that will satisfy this relation in the real number line. But complex functions, that's another story. But then even then in complex functions, the notion of positive and negative, they are not so strong. But anyway, what I'm trying to say is that when we are dealing with functions that we call real functions, or for now, what I would want you is to live with just real functions. In this real function, only this subset of the set which the initial set is being mapped to is being mapped. So this is the range of y equals x squared. And the entire set, because you see, we are mapping to this entire set, though only this region is getting mapped. We are mapping for this entire set. So this entire set is called the codomain. The codomain and range may be the same, but it's not necessary. If I was to remove this and if I was to write it like this, then the range and codomain would be the same, because codomain is the set that we are mapping to and the range is the subset that is being mapped. So both of these, for this function from A to B, for this particular A to B, the codomain and the range happen to be the same. Okay, range once again, fine. So if we think of terminologies, what does a range mean? How far can I get? How much in some sense can I get? That is what range means, right? So, let me think of a function. Could somebody give me a familiar function, please? Sorry?
Y equals mx plus b.
That is way too familiar. Sorry?
Why should you?
Why is this? No, I'm trying to get to a function that has a different range in code, but thank you very much. So, what's your name? Thank you, Ravi.
Sir, sin x.
Sorry?
Sin x.
I was exactly thinking of sin x. Who said that? Thank you. What's your name again?
Utkarsh.
Utkarsh. I have a very good friend of mine named Utkarsh in my hometown. So sin x looks something like this. So this does not look like sin x, but that is my attempt at drawing sin x. So the limitation of sin x, and if you are not familiar with sin x, we are going to be discussing that next as well. Probably after I have given you a break, because I can see most of you are getting bored. If you look at it, for every x belonging to real number, sin x is defined, right? So the entire real number is the domain of sin x. That is, it is the set from which we are mapping. And which set are we mapping to? The real number. So the real number is our codomain. And for those of you who are being confused, it's not necessary that A and B should be the same set, but they can also be the same set, as in this case. In this case, your domain is the set of all real numbers, and your codomain is the set of all real numbers as well. Right? So, the codomain here, that is the set that we are mapping the domain to, is our codomain. But if you look at it, it only gets mapped to this subset. That is, you cannot find me an x for all the values greater than 1, and you cannot find me an x. You cannot find me a y greater than 1 or a y less than 1 for which I can find an x in the domain that would map to it, right? So the point I'm trying to make is, range is the value that the function reaches. This value, the sin x achieves all values in the interval -1 to 1, closed interval -1 to 1. So that is its range. Like I said, range is how much you can reach. So sin x can reach from all the numbers from -1 to +1. So therefore that is its range. But its codomain is the entire real number, because that is what we are mapping it to, at least when we plot it in the Cartesian plane. And this is our domain because we are mapping the function f using this, that we are mapping elements from this domain to the codomain in the Cartesian plane, that here is the real number. And for every element in the domain, I am getting some element in the codomain. And then, as Lucky said, I would also like to mention the equation y equals to x, which is a straight line. And in case some of you won't be familiar with straight lines, we will discuss straight lines as well. But since this is y equals to x, if you notice, yet again the set of all real numbers is our domain. Our codomain is the set of all real numbers again. But here, the special case is that the codomain and the range happen to be the same. Because y equals to x, any y belonging to real number, I can find you an x. That would be the same number. 1 gets mapped to 1, -1 to -1, and so on. So that at least completes our definition of functions. What's the time right now? We are almost heading towards 7, so I'd like to give you a 15 minutes break. And sorry, yes? Sorry?
655.
Okay, thank you. Yes?
Just to be more precise, more particular, we can say that to identify domain or codomain, we can see what's the input and what's the output of function.
Yes. The input of a function is the domain. That is, it takes values. If I talk about science, it takes values from the set of all real numbers. This is the domain. Excuse me. The output that it can produce is the range. That is, it produces when I enter all real numbers in sin x, I notice that it always lies in the interval -1 to 1. So that is the range. but it's being mapped to this codomain, the set of all real numbers. So that is my codomain. That is, this is the entire set that is getting mapped. So, sorry.
You can identify the graph which is codomain and domain.
So if you want to identify a graph, though, you'll not always work with the set of real numbers, but per se, if you were to identify, so if you draw a graph where your x belongs to the real numbers, your entire real number must be a domain for the function to be defined, because like I said, every element of the domain must be mapped. So your domain, when you're dealing with the Cartesian plane, which is something that we call R2, because if you look at it, what R2 is, that it is the ordered pair of all real numbers. That if I take a random point here, I have got x comma y, which belongs to real numbers, where x and y belong to real numbers. And I have got that for all points. Any real number you can give, any two real numbers, and I can give you a point in this set. So this is something, basically the whole Cartesian plane is nothing but just r cross r, because every real number is being mapped to every real number, and that is the graph of this entire plane. The Cartesian plane, sometimes you hear the term R2. You'll see this term. All this means is the Cartesian plane. And as for this is the graph of y equals x square. This is my domain, the set that I'm taking the input from. This is my range, the all real numbers greater than equal to 0, because those are the value my function is achieving, right? And this entire thing is my codomain, because I'm mapping it to this, this set. Because if in R2 I was to all of a sudden map y equals to x, I would also get the negative values. But here I'm not getting the negative values. So this happens to be the range, and this entire thing happens to be the codomain. So, yes?
It's important to have inputs mapped, but if there is not any output mapped, is that okay?
Yeah, it's completely fine. So if I remove this 4 is to 4 maps to 8, and I introduce 4 maps to 7, this is still a function. The only two properties that it must satisfy is that every element of A is mapped, and that it is only mapped to one element from B. That is, 1 cannot be mapped to 5 as well as 6. 1 can only be mapped to 5 or 6 or 7 or 8. If these two conditions are being satisfied, what you have, the mapping that you have made, that is what we are going to call a function. So now I'd like all of you to have a 15 minutes break. If somebody has any doubts, they can walk up to me here, and then we'll resume the class after the 15 minutes break. So anything related to inertial or non-inertial system that somebody here did not understand? Yes.
Like they repeatedly exclamate the conditions so much that it combined happen more confusing to me.
Okay.
So just you can just briefly simplify this.
So let us, are we willing to simplify the conditions for an inertial system? Yes or no? Anything? Any response, guys?
Yes.
Okay.
But can we?
What?
But can we?
That is the question. But can we? But can we? Are we recording or shit?
Yes, yes.
Okay. Thank you. Let us assume that we already have an inertial system. I call that inertial system I. And I have an object O. And this is us, S. So the first problem that we are going to try to solve is that if we already know of an inertial system, can we figure out all other inertial systems? So all of you know a bit of vector addition, or do you want me to go through it? Fine? Please excuse my drawing. So this is the position vector of S with respect to I. This is the position vector of O with respect to I. This is the position vector of O with respect to S. So by the triangle law of vector addition, I can write that R of S with respect to I plus R of O with respect to S is the same as R of O with respect to I. Everyone find it here? The position vector of S with respect to I, O with respect to S, when added, gives me position vector of O with respect to I. That is exactly what I wrote here. I write R for the position vector. And now I double differentiate it with respect to time. now I have double differentiated it with respect to time. So what I get is the acceleration of s with respect to I and the acceleration of O with respect to s when added gives me the acceleration of O with respect to I. We are finding here, and if I send it there, that is what you would have studied in your coachings as relative motion. That is, acceleration of s with respect to I is the acceleration of s minus the acceleration of I with respect to some other observer O. Because acceleration of OS goes that side, it becomes minus OS, and acceleration, the negative of acceleration of O with respect to s is the same as the acceleration of s with respect to O. So that is what we have here. Now let us see. So we have this. If we did not get the relative motion part, it's fine. We do not need it. But what I'm trying to say is that definition of the inertial system, because I believe Professor Shi would have definitely told you this. That is, the second law says F is equals to ma, which tells me that if A is 0, F is 0. And the Newton law is just a restatement of that. The Newton law says that when no external force acts on a body, it moves with constant velocity, which means with zero acceleration. So then why do we need the first law for? Well, in order to identify the bodies for which the second law is applicable. You guys have done questions like this, that there's Varsit standing in an elevator, there's a block, that's Shwan standing here, this is accelerating upwards with some acceleration equals a naught, or if we were to say it a naught y cap, if I define the y-axis upwards, upwards. So what you would have done is, if I assume, because that is why I said we'll have to assume an inertial observer first. I assume Shivansh to be an inertial observer, and then as for Varsit, what Varsit sees is that there's mg downwards and there's normal upwards, and these two are equal, since with respect to Varsit, the block is still in equilibrium. But when Shivansh does the same thing, he says, well, it's accelerating upwards, so by Newton's second law, m minus mg must be equal to ma. So one guy says n equals mg, one guy says n minus mg equals to ma. Both of these cannot be true simultaneously until we put m equals 0, but that's a trivial case. But anyways, what I'm trying to get to is that Varsit cannot apply Newton's second law. He cannot apply F equals ma because he takes into account both the forces, and with respect to him, there is zero acceleration. And when he writes the Newton's second law, he finds out that he has done some mistakes. So that tells us that Newton's laws are not applicable to all reference frames. There are special reference frames which we call inertial reference frames, to which Newton's law is applicable. That is the job of the first law. What the first law tells us is, if the force on an object is 0, because there are four types of forces, there's gravitational, there's electromagnetism, there's strong nuclear force, there's weak nuclear force, and we know what factors they depend upon. For example, we know that if two objects have mass, through gravitation they must attract each other. If two objects or two particles have charge, due to electromagnetism, they are either going to attract or repel each other. So we can actually determine that whether F is equals to 0 or not. Do we agree on this? And Newton says that if a reference frame, if it determines that I look at an object, there's no force on it, that is, it is an isolated object. Hypothetically, that is not possible, because the black hole in a galaxy that hundreds of years light away is still attracting you. But then in physics we use a lot of approximations. So we would say that let us assume for a moment that we can still find an object so isolated or so symmetrical and this is left an exercise to the reader to figure out why something kept at the symmetry of the universe might have no external force on it, and we do not know of any such symmetrical points. But if f equals 0, if an object has f equals 0, and you notice that its acceleration is 0, then you are well prepared to use the second and the third law. Are we clear on this? Yes.
What my doubt actually is, Professor Shield continuously said that if we are saying what you also said, that first law tells us about the bodies on which the second and third law is applicable.
Yes.
So he said, when we are saying this statement, first law becomes a condition. So why don't we call first law as a condition of second law? Why is it a separate law?
No, it is not law. Well, then we'll have to ask the question what a law is. A law is similar to principle of superposition. You cannot prove it, it just works. And apart from it, well, the point is that Newton was not so ignorant that he would leave you with three statements and then he would become so-called the master of physics per se, at least the most well-known physicist to have ever lived, at least of our era. So the thing here is that a law simply is an observation that you make. What Newton did was, Newton, if you go to your library and if you search the library catalog for something that's called Principia Mathematica, that is when translated to English called the Mathematical Principles of Natural Philosophy, Newton wrote you a book this big. But then people wanted to save their money, they encapsulated it into 3 laws and gave it to you. Newton was very clear about what the first law meant. He did not directly write these as laws, though they were somewhat written as laws. But Newton was very descriptive regarding these laws as compared to what you see in the textbook. And Professor Sheet will most probably, because he did the same for us, will most probably show you another corollary, which I mean is the consequence of inertial systems, that in the Newtonian world, the way Newton viewed the world, the way the Newtonian model works, time is absolute. That is, if you are here, those of you who have watched Interstellar, if you are near Gargantua, it was something like that. Yeah, what? Gargantua. So I'm pronouncing it right, fine. So if you are near Gargantua, according to Newton, if our clocks are synced, 1 second would be the same for us. But for those of you who have not watched Interstellar, first of all, please watch it. That's a prerequisite of this class. This class is only one prerequisite that you need to watch Interstellar before coming here. So if you watch it, what we observe is that the time actually varies. Time is not universal. As to say the way Einstein would have put it, because Einstein was the guy who proved Newton wrong, at least Newton's notion of absolute time wrong. The way he would have put it is that there is no master clock as to speak. It's not like there's an audible tick-tock across the universe. For me and for you, time can be different. So the point is, Newton wrote it in a very descriptive manner. After all, he has got a whole book on it. He even discusses celestial mechanics using his laws. But then we'll have to deal with what we are left here. It's similar to how mathematicians named this thing as, they named numbers of this sort, or at least I should write of this sort, where x is a real number, imaginary. They are not imaginary, they are very real. The more you advance in physics, the more you'll have to use these so-called imaginary and complex numbers. In fact, there's a huge philosopher and a great mathematician as well, which after whom we have named the Cartesian plane, René Descartes. And if you have not heard of him, I believe most of you would have heard a quote from him. I think, therefore I am. That is what René Descartes remarked. Oh, it's very interesting, but I would not recommend you to read it. You have got a lot of fun stuff, other fun stuff to do. But René Descartes, as mocking, as some sort of mockery, called these numbers imaginary, and they stayed that way. It was not a mathematician who was serious about it that named it imaginary, because these numbers, they happen to be very real, but You can call it a misfortune that it is the way it is. So that's the same thing with Newton's laws. It is the way it is. However, it is a condition which tells us that on what bodies can we apply the second and third law, or what reference frames, standing in which reference frames we can apply the Newton's second and third law. So this is the condition of an inertial system. That is, when I looks at O, if there is no force on O, that is O is an isolated body. There are three bodies in the system, so it is not isolated. But let us believe it's so far off, and it can be very well approximated to 10 to the power minus 30, 40, 50, whatever, to be isolated. So, and there's no force on it. So what I would see is that since I is an inertial reference frame, O has no force acting on it. So acceleration of O with respect to I is the vector 0. And now we want to determine the condition under which S would be an initial reference frame as well. The condition remains the same. So then the acceleration of O with respect to S must be 0 as well, because on O we have no force. That is why we could write 0 here. So then I write acceleration of O with respect to S as 0. So then ASI is 0 as well. That is, if we have an inertial reference frame to begin with, any other reference frame I can look at, and if it's not, if I am an inertial reference frame, and I look at any other reference frame, by reference frame, it is a very technical word. What we mean is an observer. If I am an observer, an inertial observer, and I look at any other observer, and I see he is not accelerating with respect to me, I would say he is an inertial observer as well. But the question remains, you assume this came out of nowhere. How do you know that? We believe that. That is the problem. We believe, or you could say experimentally, because why do you believe principle of superposition? If it did not work, you would not believe it. Professor Sheath told us that experimentally we have seen that, yet again, because forces are something that you can calculate, that if a body is isolated, it has nothing around it. So you can say that it is the first absolute inertial observer, and using this body, you will talk about all the other reference frames. Using this one body, you will determine every other reference frame, whether it is inertial or non-inertial. Newton was a very smart person, at least smarter than me, I know that. So Newton said that I claim that the distant stars, because how about this? If I look at you, right? If, sir, could you get up? Keep your back, please. And I stand here. Move 3 steps to the right. 1, 2, 3. So I look here. Somebody from the back. Person. Oh, nothing. Varun, please stand right in front of me in the back. Everybody, eyes on Varun, please. Move 3 steps similar to how Sharda moved. 1, and over 2, and over 3. And now, because Sharda was closer to me, so though he just moved 3 steps, I have to look here. And though Varun was far away, assuming that the steps were equivalent somewhat, I only need to move this much. So I need to move this much when Varun is there. I need to move this much when I want to look at Sharda. Sharda and Varun, please. Sharda, thank you so much. So the point is, the farther something is, even if it's in motion, it is difficult to detect its motion. And like we said, no body is isolated. So we'd have to approximate an absolute inertial observer anyways. Because though it is incorrect, Newton believed this law. So no matter how big of an R, M1 and M2 you keep, you will find a finite F, a non-zero F. So Newton said that no matter, he himself said that no matter, even if there are particles across the ends of this universe, there is still going to be a non-zero finite force between them. So Newton knew it better than anybody that there could never exist an actual absolute inertial observer. So Newton knew we need to approximate it. I should say Sir Newton, please forgive me. I'm disrespecting him, but yeah, because I have to say it so many times. So when I say Newton, that means Sir Newton. So what Sir Newton did was, he said that when I look through a telescope, the most distant stars, because of course the technology back then, the telescopes were not so great. They are not so great even today, given the expanse of the universe. But of course, we have made tremendous, almost exponential progress. But when we see through the naked eye, and at that times I believe even through telescopes, some stars would be so distant that even if they moved, they would appear to be still. Newton said, that distant star, I name my absolute inertial observer. Problem solved. This is the distinction between inertial and non-inertial observer on your level. However, as always, there's a question, and it's been very unfortunate that I myself have not been able to find an answer to this. So if you do, please do tell me. That is, and I wanted to talk to Professor Sheet about it, but it's just been that we have not had the opportunity to meet in a very long while because he's so busy, and now he has even your responsibility, so he's even busier. Question is, you assume that forces do have a physical origin, that you believe that gravitational force is real, electromagnetism is real, strong nuclear force is real, weak nuclear force is real, as if what you're saying is forces are something which have a physical origin of sorts. But can you see a force? What do you see? And what is the effect of a force? So don't these two mean the same thing? And there's an and between them. So if we remove our assumption that forces are something which have a physical origin, these two mean the same thing, and therefore you cannot add an and here and use it as a condition. That is the question. But I believe, at least until this point, because I have not found a better answer. And in science, especially in physics, you never get an absolute answer, because Newton, as great as he was, as perfect he was still flawed. His theories turned out to be incorrect, or at least a less than perfect model of reality. So the point is that we assume that forces, they have some sort of physical origin, and at least I believe until now that is how you claim this to be a condition for inertial observers. Now I do not know whether or not that is true, and that is for you to figure out. Like I said, I am no better than you, I am no smarter than you. It is my responsibility to give you everything that I have and hope that you can make something better out of it. That is how science has always worked. As Sir Newton has said, though there are some remarks that he rather said it to somebody who was a rival of him, who was short-heighted, somebody by the name of Robert Hooke, but still it's a great statement. He said that I see farther, I'm roughly quoting, but it's not exactly his quote. I see farther as I stand on the shoulder of giants. And that is what science is all about. You cannot expect, if you are not a superhuman at least, in your lifetime to discover everything from scratch. Because there are people like this, and this is something that happened a lot in schools because we were preparing for the exams. Sorry, I'm talking about something more philosophical in nature rather than study, but this is important, I believe. There were questions which were dealt a certain way, and the first thing that popped in my mind was, मेरे दिमाग में कैसे आएगा कि ऐसे करना है? That is a very natural question that comes to all of us mind. That fine, a mathematician has told me this, you are telling me this, but How would I have come up with this? The answer is you couldn't have come up with it. That is exactly the reason why you need your elders, you need your ancestors, you need Sir Newton, you need Sir Einstein, you need Sir Maxwell. And these are just to name a few. There are names that we don't even know of who have been heroes of science, and I will leave you with that thought that in order to do science, be prepared to stand on the shoulder of giants, respect the giants, but never show undue respect, question the giants, and be better giants for the upcoming people to stand on. Thank you.